Hello, all will start in 5 minutes. Okay, welcome everyone. We'll kick this off. It's with great pleasure that I welcome Rajalashmi Nandakumar, who is an assistant professor at Cornell Tech. And I remember the first time I met her because she was doing this, she was presenting this amazing work on wireless, contactless smartphone sleep apnea. I know that work has gone a long way, but I still remember her at that time. So I'm very honored that she has accepted our invitation to be here and present. Without further ado, please take the floor. Thank you very much.
Thank you. It's actually great to be here. Um, as she said, I'm Rajalakshmi Nandakumar. You can call me Raja. I'm an assistant professor at Cornell Tech. I lead the wireless sensing and mobile systems at the Tech campus. Um, okay. Okay. So my research focuses on leveraging the wireless sensors in everyday smart devices and using the wireless signals from these computing devices to enable various sensing capabilities. And we then use these wireless sensing technologies to enable applications across different domains. Some are mobile health, the other domain are digital agriculture, or what we call precision agriculture, and then like some involves building new user interfaces. Um, okay, yes, sorry about that. Okay, so um, in this research, I'm actually going to focus on some of the works that I had like previous in mainly in the health domain, some of the works that I have previously done, some that are actually like current works, that's current exciting things that we are actually doing in our lab. Some are like well-known papers, some are like in submission. So yeah, feel free to ask me any questions. Okay, so in the research that in today's talk, some of the topics that I'm planning to discuss are mainly like how to enable computational wireless sensing and how we can use these wireless sensing technologies to passively monitor physiological signals. Regarding this, early in my PhD, I worked on a couple of projects where we actually use the acoustic sensors in the smartphone to detect the breathing motion of a person in a contactless fashion. And once you can determine the breathing signal, you can actually then use this physiological signals to monitor various conditions. The second project, which I'm currently like working on, is how can we enable the same how can we enable the same wireless sensing in actually a privacy preserving manner. So in order to show that, we are actually like currently working on building wearable sensors that could enable privacy aware wireless sensing. So this is actually a small video of this a wearable mode that actually like mimics like a heartbeat, which can actually like then uh, which can actually like prevent others from like monitoring your actual heartbeat. So I'll discuss this in detail again in the second part of my talk. There are other projects that are currently like going on in my lab. One of them, again, close to completion, is trying to understand the effect of extreme heat related events in cardiac health, specifically on underserved communities. You can see that global warming is a big issue, and like every summer, you're kind of like seeing the temperatures going through the roof. Every day in New York last year during the summer was like a record breaking temperature. And for people belonging to the underserved communities, they actually like live in buildings where they're exposed to these extreme heat related events. And that actually causes significant risk to their cardiac health. So one of the projects that we're working on is how we can monitor this and how we can kind of like track this effect of the events on the cardiac health. Okay, so these are like some samples of like projects that we have been doing in our lab to give you an idea of like what we do. Okay, so in today's talk, there are like the two main projects that I want to focus on is the wireless sensing for physiological signals, as well as how to do it in a privacy preserving manner. Um, so I looked at like all the talks in the series, right? Like one thing is like there's like multiple hearables, wearables, different kind of like stuff. So I wanted to kind of like see whether we can introduce wireless sensing, right, to in this seminar. So, what is computational wireless sensing? This is actually the bread and butter of what I do. And when someone asks what computational wireless sensing is, and for any layperson, the video I kind of like always show is this one.
Beautiful. You've turned every cell phone in Gotham into a microphone. And a high frequency generator receiver. You took my sonar concept and applied it to every phone in the city. With half the city feeding you sonar, you can image all of Gotham.
Yep. So when we started kind of like working in this area, that was this ultimate goal, right? Like, can we actually do what was stated in this Batman movie? That is, can we actually take the smartphones, turn them into, this active sonar device where you're actually like sending the signals, looking at the reflections, and can you actually image the entire environment? Right, we are there and not there, but yeah, let's so we kind of like take more and more steps over the time towards this kind of like lofty goal. Okay, so towards this, the first project we looked at was how we can use this wireless sensing concept to actually detect the breathing of a person, right? And we ended up building the first contactless breathing monitor by transforming these existing like smartphones that we all have into an active sonar system. So, what do we mean by that? Now, the idea is simple. You have a smartphone, the smartphone has a speaker and a microphone, right? So, you send custom signals using the phone speaker. These signals are reflected by all the objects and all the subjects in the environment, right? So if someone is sleeping nearby or someone is like sitting in front of the smartphone, the signals are going to actually reach them and these signals would be reflected by the person. You then take the signal that is being reflected and record it in the smartphone's microphone. So the cool thing is that when you're moving, or let's say when you're breathing, you're inhaling and exhaling, and your chest and the abdomen moves, right? So if when the signal is reaching your body and when the chest is moving forward, the signal is going to be reflected like earlier, and it's going to actually reach your microphone earlier. But when your chest is actually like pulled, the time it takes for the signal to come from the speaker to the body and then back to the microphone is going to take a longer time. So if you actually record all the echoes over time, process them, and kind of like look at the signal that comes over time, you would actually be able to get this periodic breathing motion. So that's the concept, right? Like we take the smartphone, we use the existing sensors that are already available in the smartphone. We send this inaudible sound signals, receive it, and then process the echoes to actually get the signal. So like when I explain this, it's like very simple, right? Like use the devices, just send, receive, simple. But when we actually implemented this in practice, there were like multiple technical challenges. The first one was that the signal was not only reaching the body, but it would just go through kind of like it would be reflected by all the objects in the environment. So the first thing is you need to kind of like filter the signals that are coming from the person. The second challenge is you need to extract that breathing signal when you kind of like have no idea about the environment. You don't know where the person is. The person could be moving over time. So it at every time instant, you need to be able to locate the person and then extract the breathing. The third one is you need to like operate it when there are actually like multiple people in the room. The fourth one is making it work across like different devices with like different speakers, microphone specification, etc. So at a high level, this is what we ended up doing. So we sent this inaudible sound signal. We actually kind of like received the signal, and then we started like processing the reflections that we got, right? So the goal is you want to start looking at the reflections that are coming from every distances, right? You start at zero distance and then you start looking at it for increasing distances. Now, when you actually like get hold of the periodic signal, which is typically your breathing signal, you can kind of like stop the search. When there are multiple people, you keep on continuing the search till you look at like some maximum range that you have defined for your system, right? So this is kind of like the high level plan. In order to execute this high level plan, you need one main thing, which is the ability to separate the reflections that are coming from different distances. So, in order to do that, this is kind of like the system we went with. We had the phone, there is actually a person sitting in front of the phone. We sent custom signals called the FMCW signal, which is a frequency modulated continuous wave signal. And this signal, the speciality of it is that the frequency of the signal increases over time. Okay. And in this case, we are actually like sweeping between 18 to 22 kilohertz because that signal is actually inaudible to most of the adults. So we transmit this signal and then you're going to get reflections. The thing is, the great thing about the FMCW signal is that any difference in any time difference that you're actually like seeing between the transmitted signal and the reflected signal, which corresponds to basically the distance the signal has traveled, is actually translated into a frequency difference. Okay, so basically what's happening is that every time difference or every reflection from every distance corresponds to a unique frequency difference. Now, why is it great? It is great because it's actually easier to measure the change in frequency in the frequency domain compared to measuring time of flight. Okay, so that is why we actually use FMCW signals in this case. So in this figure, as you can see, you're going to get multiple reflected signals from both static objects as well as the person. And for every received signal that you have like a unique delta F. So if you actually like take those signals and take an FFT, which is fast Fourier transform, which basically takes the signal and then converts it into the frequency domain, you're actually going to see different bands corresponding to different distances, right? So there is going to be like one set of reflections coming from the coffee mug, there's going to be one set of reflections coming from the wall, and then there is going to be like one set of reflections that are actually like coming from the person, which constitutes the breathing signal. So in this way, we are able to actually separate out the reflections that come at different distances, and we are actually able to monitor the person's breathing in a regular like environment with like multiple objects. Now, the same thing can also be extended to multiple people, right? Like if you have two people, hopefully if they are at different distances, then their breathing signals are going to occur at different frequency bands. So you will be able to monitor their breathing signals simultaneously at like two different frequency bands, right? So in this case, as you can see, they are at different distances. You're going to have different reflections, and you could actually like measure that simultaneously, right? Now, sorry. So with this, you can see that you can use like an everyday wireless sensor, which is basically the acoustic sensors in your everyday device, like a smartphone, to actually wirelessly monitor someone's breathing motion, right? Now, you can take the same concept and actually say that I can not only wirelessly sense breathing motion, I could probably detect every other motion that's happening in the environment as well, right? So, some of the works that I have done actually kind of like shows this. So, this is like one project where we are actually using the same concept to detect the finger motion. Um, sorry. Wow. So you can see here that when your actually finger is moving, you can use the speakers and microphones in your everyday devices like smartphones and smart watches to actually detect this finger motion. So why is this useful? This is actually useful because it increases the accessibility of these devices to new user interfaces. In fact, this kind of like wireless sensing can not only detect motion, but it could in like a very coarse way, but could also like go to an extent where it could detect motion in kind of like a very precision manner. For example, we took the same system and improved the accuracy of the wireless sensing in such a way that you can not only detect like a coarse finger motion, whereas you can actually estimate the joint locations of the every joints in your finger. So here we are actually looking at 21 joints in the finger, and you're able to estimate the exact location of all these joints of all the fingers, and especially like kind of like get something like your entire hand posture estimation, right? So you took wireless sensing where we started with something as coarse as looking at like a breathing motion where your entire chest is moving, then you can actually like improve the accuracy to such a way that you can actually detect like a finger or a hand motion. And then we have now kind of like pushed the accuracy to such a level that it's not just finger, but you can actually detect individual joints in the finger. So as you can see, we are kind of like the research in wireless sensing has been advancing over the years to actually enable more and more accurate sensing. And this can be used in a lot of applications regarding health. For example, one of the things that we are doing with hand motion is to detect Parkinson's. Can we actually detect tremors ahead, like even when they are actually like very minute? So, if do we even have the accuracy for that? Right? Can we actually detect facial expressions and facial like changes, the muscle movements, right? So we now have the capacity or basically the accuracy to do a lot more like precision sensing. And we also call it like multi-part sensing, because in this case, even when you have like multiple like fingers moving at the same time, you would be able to detect all the joints at the same time, right? So what we are trying to do here is to kind of like improve this like multi-part sensing and improve the accuracy to a millimeter level precision, so that we can actually like use wireless sensing for various applications. Okay, so the another one I just wanted to actually like add this here is because this one might not be exactly related to health, but the one thing I wanted to add here is that you can use wireless sensing not only for like motion sensing, right? Till now we had looked at motion, either it's like breathing motion or it could be like, hand motion, finger motion, etc. But it was looking at motion, right? But you can take a next step, and like you can also use the same wireless sensing mechanisms to actually even detect static objects, or basically like the composition of like objects. For example, you can determine whether an object is metallic, right? Or like what is the composition of that object. For example, one of the work we recently did was that we used RF-based wireless sensing mechanisms to detect if a soil sample is actually contaminated with lead. So wireless sensing can actually like just look at this. It could basically like look at the soil sample. Like in this case, we are actually using a USRP based device to send frequencies of like multiple signals, multi frequency or multi band RF based signals. We are looking at the reflections of these signals by the soil sample, and we kind of like show that you can estimate the amount of lead in the soil. Specifically, we are kind of like seeing whether the soil has like lead above like a certain range, which becomes like dangerous for people to interact with. This is actually one of the serious problems in New York City. A lot of like areas have soils that are heavily contaminated with lead, which causes like lot of issues, or like lot of like health conditions specifically for kids, because kids interact a lot with soils, playing in your backyard, playing in the playgrounds, etc. So this kind of like system can actually be used to detect the lead contamination in the soils without using some complicated kind of like instrument. So why wireless sensing? One is that if you look at the trend of the wireless sensors, right? It could be like either acoustic speakers or microphones, or like RF based, which could be like Wi-Fi up till or like RFID, or like up to even your millimeter wave technology, which is becoming more prevalent now. You can see that the trend is showing an increasing number of these devices all over. Pretty much every devices now have speakers and microphones. The number of speakers and microphones are also increasing to a higher rate to increase the accuracy, right? And pretty much like all devices, even your regular devices are now becoming smart devices with Wi-Fi chipsets, right? And there is talk of like having millimeter wave chips in like potentially all devices. We know that Google kind of like started it with its Google Pixel, but now people are talking about adding millimeter wave chips to multiple devices, right? So you can see that a lot these kind of like wireless sensors are becoming ubiquitous, and there are actually like more number of like these sensors in everyday devices. The second thing is that depending upon the wireless technology that you choose, either it's like acoustic or whether it's RF based, you can actually like see a varying, you can actually like achieve like high accuracy, or like you can achieve range. And it's actually like it's actually kind of like a tuning parameter that you can use, and you can actually like enable various applications using using this technology, right? And for example, to elaborate, if you use like an acoustic sensor, you know that because the speed of the sound is actually like small, or it's only like 340 meters per second, you can actually get very high accuracies, like millimeter level, using just your existing speaker and microphone in your device. So we are talking about like an accuracy of like 7 millimeters, like nothing, just using your regular speaker and microphone, which is not even kind of like improved for like this kind of like sensing technologies, right? Or if you want range, you can use something like Wi-Fi, right? Where you get larger ranges. You would be able, researchers have shown that you could actually like monitor these signals even beyond the rooms, like for people like across the walls. So depending upon the wireless technology that you use, and you can actually like tune the accuracy and the range of this particular system, and you can develop like application for like various real world scenarios. Now, the third important advantage of wireless sensing is actually passive monitoring. So you can enable passive monitoring of these signals or these motion for like multiple people without you requiring them to kind of like wear something, right? Like no wearables, no need to like charge these wearables. There is not, the retention factor does not become an issue here. So you already have these devices with these sensors, and they can monitor you in a contactless fashion, right? This is important specifically for people, elderly people who kind of like hesitate wearing stuff or like forget wearing the wearables, like the wearables or watch or like other devices. So these are all the great advantages of wireless sensing and can actually, as I said, enable different applications. Okay, so I told you like how wireless sensing works, gave you an example of like, how you can get, for example, how you can get kind of like a breathing motion using that signal, where you could use this method to actually get a particular you can get breathing motion for multiple people at the same time, right? And you can pretty much we can use the same concept for detecting like different motion, and the concept also remains kind of like similar even if you use like RF technologies. So once we kind of like saw how we can build this wireless technology, we started developing various applications specifically in the health domain in our lab. So the first one that I worked on, which Cecilia actually mentioned, was to build a sleep system, a smartphone-based system that could actually diagnose sleep apnea in a contactless fashion. So we took that technology, the one that I showed, which can detect breathing, and we used that to actually like detect the breathing signal over the night when the person is sleeping. And we were monitoring these breathing signals and identifying these breathing disorders that could occur during sleep. And that's what sleep apnea is. Sleep apnea is basically breathing disorders, like someone like not breathing well, or someone like stop breathing during their sleep. These are like various disorders that occur, which determines whether a person has sleep apnea or not. So we took the technology, that breathing monitor, and the first application that we enabled was to diagnose sleep apnea using a smartphone. So this technology was, we tested it in a sleep lab, Harborview Medical Center at UW Medicine, and we showed that we were able to actually detect these respiration events, disorder events. And this technology is licensed and is now available um, in the app stores. So yeah, what are the other things that you could do? The one project that I'm still kind of like working on is using this kind of like breathing sensing technology to detect opioid overdose. As you all know, opioid overdose is a public health epidemic. It's a leading cause of death for people before age 50. And one of the biggest thing is that 93% of the overdose deaths can actually be prevented by injecting naloxone, which is the antidote. But the problem is that in most of these cases, these people are actually alone and they are not diagnosed at the right time. And only 6% of these victims actually get access to naloxone. So, what we need to do is you need some way of detecting these opioid overdose when either they are alone or whether they are amongst the untrained people. So there is actually a need for a system that can detect opioid overdose and rapidly connect them, like either like call 911 or some loved ones who can actually get naloxone. So how is it connected to breathing? That could be the first question, right? So to give you an idea, this is what is an opioid overdose. As you can see, when someone injects an opioid, what happens is that it kind of like gives a signal to the brain, and the brain kind of like the part of the brain actually goes to sleep. And when that happens, the person actually stops breathing. So the first thing that happens is the person going to sleep and actually like stopping breathing. So that's what we call as apnea. Okay. And then once the person stops breathing, over time, their oxygen saturation levels will drop. And when it actually drops to an alarming rate, they're actually going to get cardiac arrest, and that leads to fatality. So as you can clearly see here, the first thing that happens in this scenario is the stopping of that respiration. So if you are able to actually detect this stopping of respiration early on, then there will be enough time to actually provide that intervention, like calling 911. Right. So that is why we kind of like saw that such a respiration monitor can actually be used to detect opioid overdose in a timely manner. So we built a system called Second Chance. It is a smartphone system that actually detects opioid overdose and its precursor. So here is the photo of the app on the smartphone. And we actually tested the system in a supervised injection facility at Vancouver. So this is a facility where people can bring illicitly obtained drugs and they take it actually in front of trained physicians or trained medical professionals, basically. And one thing we did was that we took our smartphone app to this facility where we placed the smartphone app in front of them when they were actually like injecting the opioids. And we were then actually monitoring their breathing and trying to detect like two things. One is central apnea, or basically their cessation of breathing, and we were also trying to detect opioid overdose. So we kind of like tested the system with about 200 patients over there. We use like a regular respiration belt as like a baseline, and here is the protocol. And when we were looking at like cessation of breathing, we got a very high sensitivity and specificity of detecting these occurrences. Basically, like we were able to detect when a person stopped breathing and when kind of like it needs to be alerted by when this particular event needs to be alerted to the professionals, the medical professionals over there, right? So we actually had a very high accuracy in detecting the cessation of breathing. Specifically, we were looking at like a 10-second window, like someone at least like stop breathing for like 10 seconds. So that was the goal we were looking at. So the sensitivity and specificity both was about like greater than 95 percentage. So we asked a question, like if we kind of like implement this system in the real world, like how would you do it, right? Um, to give you an idea of what happened, here is the histogram that actually kind of like shows these kind of like breathing stoppage, which we call as a central apnea event for like people. So you can see that for a lots of, so about like 40 times the person's breathing actually stopped to either like stop for 10 seconds or 20 seconds, right? And in some cases for about like 10 people, um the 10 times the breathing kind of like stop even for like 30 seconds or even up to like 40 seconds. Only for like there were two events where the breathing actually like stopped for more than a minute. You can actually like see that in the histogram. To add more notes, when we were doing this study among the 200 people, there actually happened like two overdoses, which required intervention by in the means of like injecting naloxone. But in all the other cases, there were like cessation events, like a lot of people had like cessation events. And in fact, like 80% of the people who had cessation events had actually like stopping of breathing off up till like even 30 seconds. But then after stopping their breathing for 30 seconds, they just kind of like woke up. So what we did was that you can clearly see here that if like if you wait till like some amount of time and then kind of like report it, right? Like if you actually like start your alarm or even like calling 911 when they have only stopped breathing for 10 seconds or 20 seconds, then what's going to happen is you're going to actually create a lot of false positives. So you need to have like a plan of like when to intervene. So what we were kind of like seeing here is that people stop breathing when they take opioids, but it doesn't mean that all people who stop breathing is actually going to end up in an opioid overdose state. So we need to like in some way take this breathing cessation signals and see like in what cases would we need to like alert, or in what cases do we actually need an intervention, right? So, in order to determine that, we looked at this data, and here is the interactive system that we actually proposed. So, as you can see, pretty much the danger zone kind of like starts mostly after like 30 seconds. So, we kind of like said that we will raise an audible alarm or some kind of intervention only when the person has stopped breathing for at least 30 seconds. Okay. And even in this case, we are only raising kind of like an audible alarm, like an alarm on the phone. So if this alarm is activated and the person like if it makes the person to like wake up and like be okay, then they can de-escalate the alarm by just pressing a button and turning off the alarm. But if they could not wake up and if they could not de escalate it, then you know that there is a high chance that the person is experiencing overdose. And in that case, you actually like escalate the alarm and call 911. So, and or like either like a 911 or like a friend who would potentially have naloxone. So the one thing that you could see here is that for this application, though breathing actually like works out great in detecting kind of like the precursor for opioid overdose, we need to still work on like finding this or like tuning the system to actually determine when do you actually want to like look at the signal and when do you want to intervene. So that is like one study that is kind of like still happening in this space where you need to like utilize your resources by sending out alarms only when you're kind of like absolutely sure that an alarm is needed. As you all know, 911 or emergency services is actually like a very limited resource that cannot be wasted using for potential false positives. So what is needed is actually tuning a system that could actually do it at multiple levels and call the 911 only when it's needed and at reduced false positive rate. So that's one of the things we are kind of like still working on. The other thing that I'm working on in this space is currently we want to kind of like expand the system. So in the inside, like we were doing individual monitoring. Basically, the person's smartphone was used to detect the breathing of that individual subject alone, right? So the assumption is that they're probably alone in their homes or some private spaces. They use this app in the smartphone, turn it on just in case, right? It's kind of like a harm reduction technique. What we want to actually do right now, or what we are doing right now, is basically expanding that to public spaces. So, can we have room level sensing of like multiple people simultaneously and detect opioid overdose? So, in this case, we identified that a millimeter wave technology is actually a better solution where you could get actually like room level range at a very good accuracy, an accuracy that is either like similar or better than like an acoustic wireless sensing. And we are actually like implementing this in CPAS, which is basically Complex Pain and Addiction Center in Vancouver. So we are now running clinical studies where we have this millimeter wave sensing technologies, which is monitoring like multiple people's in like rooms and detecting opioid overdose, as well as like it's also looking at behavioral patterns of people who are undergoing like opioid injected episodes. So in this case, we are actually like using more generative AI to actually like detect physiological signals more accurately for multiple people at the same time, even when some people are actually in motion. So I'm not giving too many details here, but if you want to talk about, because like, the paper is kind of like in submission, but if you want to talk about it, happy to chat about it more in private. So this is like one of the work where we are continuing looking at like opioid overdose, trying to identify the points and like also like expanding it to public spaces. Okay. Now, the other work that I wanted to slightly introduce in this case is uh, one of the projects that we are doing in our lab, which we call Vital Height. So you would have I mean, like by now you can see that we are actually doing a lot of wireless sensing, right? We use these like wireless sensors. We are detecting like breathing, heart rate. We are detecting like hand posture. We are detecting opioid overdose, etc. But all these utilities come with like one concern, which is privacy, right? Basically, now anyone can have like any of these wireless sensors in an environment without the other person knowing it. And it can actually be used to monitor this physiological signals of like other people in the environment without their knowledge at all, right? You know that there were like multiple instances where you can put these kind of like sensors in offices and like, hey, can we actually like use that to measure your physiological signals, in turn your stress and productivity? Or like, or can you actually like put the sensor in an Airbnb which can now detect your physiological signals when you go to the Airbnb, right? Where you have no knowledge that a particular sensing is actually happening. So as a responsible researcher, one of the things we wanted to look at is, can we actually enable wireless sensing in a privacy preserving manner? So the high level idea is this. We believe that wireless sensing has like multiple utilities, right? These are actually like being able to detect like breathing, heart rate in a contactless manner is extremely useful, and it can enable like interventions in kind of like the right moments, right? But at the same time, we want only authorized devices to actually like measure these signals. And at the same time, these signals should be blocked for unauthorized sensors, right? And one of the main thing here is that we wanted to work across like all wireless modalities. It could be like Wi-Fi, it could be acoustic, it could be millimeter wave, it could be RFID. Let's just go with any wireless modality. We should be able to like block all unauthorized devices which are using all these frequencies, right? So we are building this system called Vital Height. The key idea is that it is actually a motion-based solution. So what it's doing is, this is actually a wearable that can be part of your fabric, okay, or the shirt that you're wearing. And the goal of this particular wearable is to create motion that will obfuscate your original vital signal. So remember the first video I showed about it, where there was actually like a silicon mold that is mimicking the heart rate. That's basically the idea. That silicon mold will be part of the t-shirt that you're actually wearing, and it will create these heartbeat fake motions that will obfuscate your original heart rate. So only authorized devices, such as let's say it's your smartphone or your Google Home or Amazon Alexa, will actually have the key to decrypt the signal, or basically the fake motion that you're generating, and it'll be able to remove it and get the actual vital sign. For all the other devices, they will get this combination of signal, and they will not be able to detect, differentiate the fake motion as well as the actual motion. So that's kind of like how the system works. And as I said, it's actually frequency agnostic. The main thing, the reason for that is that by having the variable create a motion, the effect is going to be seen irrespective of whatever frequencies you use, right? If you send an acoustic signal and that's getting reflected, you will see the same motion in the acoustic signal as well. Or if you're sending like a millimeter wave, you will see the same motion or the fake signal in the millimeter wave as well. So you don't need like different antennas covering all frequencies, or you're not doing anything different for like different modalities of wireless sensing. Rather, by creating this fake motion, you're able to kind of like cover all types of wireless sensing modalities. So actually, due to the time, I'm not going to go into detail of exactly like how we are doing, but here is kind of like the overview where we create this up the fake signal, which we use it to generate the motions using the silicon molds, which is fabricated in your shirt. And then you can see that the authorized sensors, they have the key to remove the fake signal, whereas the unauthorized sensors will not be able to do it. So that's kind of like the idea where you can actually have this variable system and protect yourself. So you could think of the goal as that tomorrow you could probably like subscribe to a service, let's say like your telephone subscription, you're doing the service subscription, which has like devices like all over the city. It's kind of like continuously monitoring your signals and can enable interventions if you need it. But all the other devices in any public spaces would not be able to actually track you or measure your physiological signals using wireless sensing because they don't have the key. Okay, so we are kind of like now um, building like different structures to actually see which is the optimal mode, which is kind of like the more usable one to actually like wear. I have like multiple pictures of my students like wearing it and trying this out. Like happy to actually like show the fun video if you guys are interested. Okay, so that's basically like what I wanted to like cover in this talk. So want to say that wireless sensing is kind of like an amazing way to do passive monitoring of like physiological signals or other motions that can diagnose various health conditions. Recent research is actually like working on increasing the range, increasing the accuracy that was not possible before. And that has further kind of like led to various applications in this domain that is now becoming like feasible both in like private and public spaces. That's it. That's it for today. And I'm happy to take any questions.
Thank you, Raja. That was really interesting. I'll clap for everyone. If you have questions, audience, please put them in the chat and I'll try to read them out, and Raja can also read the chat. I'll start with a question that I have. So you're using mobile devices, which is great because they're in the hands of everyone. You don't have extra hardware to use. Can you tell us a bit more about possibly energy consumption of your approach?
Yes. Most of these, so the one thing is that like um some of these devices, you could kind of like have it like plugged in. It could be like, if you're using like Wi-Fi or like devices in like, these kind of like chipsets and smart devices, you would be okay with just like plugging it in. For example, if you have like an Amazon Alexa or like a Google Home, it's always plugged in, so you're not worried about the power, right? That's one. Now, if you're taking like smartphone, then yes, depending upon the application, like keeping this on for a long time does consume a lot of power. And in that case, there are kind of like multiple like smarter ways of turning it on and turning it off like over time. And like uh, looking at basically like um the so basically looking at kind of like the power budget, like to determine like when you would turn it on or when you would turn it off, you know. But in most of the cases we kind of like look at applications where these devices are actually like plugged in, like your as I said, home assistants plugged in. For if you're using your smartphone to actually like monitor your sleep, most probably you're putting your smartphone in your sideboard, which is like plugged in charging over the night, right? So in those cases, power is not kind of like a major issue. In other cases, you would basically then kind of like have cases where you have to do this over periodically and not turn it on kind of like all the time.
Yeah, thank you. Thank you. That was my thought. I have a follow-on question, but before I do that, there are a couple of questions online, so I'll read them. Matthias, thanks you for the talk, and I read what he writes. I was wondering how robust the sleep apnea detection is with respect to the person moving in the bed, since the reflection patterns would change during the night depending on the user position.
Yeah, that's a great question. Yes, it would change. One cool thing is that any motion that's happening is still tracked by the system, right? So, for example, when the person is actually moving, that moving is actually changing a cause in the reflection from the person. So, just like how you're seeing the breathing signal, you will also be able to see the motion signal in the reflections that you're processing. So you can, the first step we do is we do the processing and we look at the signal and we kind of like say that, okay, this is actually breathing signal or this is actually motion signal determining whether the person has moved or not. Okay. So we kind of like do that classification, and it's very actually what we have noticed is it's actually very easy to differentiate the breathing and the motion signal because the motion signal has much higher amplitude and it's also like more random and non-periodic signal. So once you detect that, you also kind of like mark that the person has moved. So the next time you're looking at the next time period, you're basically looking for the person in like a different frequency channel or different distance, and then you kind of like continue tracking their signal. And in specific to just sleep apnea, it is that when someone is moving, for sleep apnea, they don't actually look at physiological signals when the motion happens, because when the motion happens, it means that the person has like woken up. So the physiological signals during that timeline does not constitute. It actually constitutes as like someone waking up in the middle, which constitutes to like some disorder, right? So that is one thing for like sleep apnea. Like once you see the motion, you can clearly say that, okay, person has woke up, and then you kind of like move to the next time period. But in the other case, like more recently, now what we have been doing is that in applications where you need to know the physiological signals, even when the person is moving, like they're walking or like, you know, they're just moving their chest, etc. We are now actually building millimeter wave based systems that can differentiate both the chest and the abdomen motion and other motion. So yeah, right now we are using generative AI to actually like do that. And that's kind of like one direction that people are looking at to detect the signals even at the time of like other motions like leg movement, etc. I hope that
Thank you.
answers your questions.
I think it does. Adam is also thanking you for the talk and is asking, could you explain a bit more about how the lead content was detectable in your soil system?
Sure. So the concept beyond behind that is actually dielectric permittivity. So what happens is that when you transmit a frequency, an RF signal of certain frequency, this signal passes through the soil and gets reflected, right? Now, the received reflection depends upon the power as well as like the time it takes, both the time it takes to go through the soil as well as the power, the reflected power depends upon um, the dielectric constant of the composition of the soil. If there is more water, that actually affects it because water has a high dielectric constant, right? So the dielectric permittivity is a key factor. So what you could do is the presence of actually lead affects the dielectric permittivity and in turn actually affects the reflection of the signal, both the time taken for the signal to pass through as well as the power of the signal. And what you could do is then use this measurement and kind of like train your system to detect different compositions of the lead based upon this reflected signal that you're seeing. That's what we did at a high level. We took soils and we actually of different compositions and we started spiking them with different levels of lead. And then we sent frequencies of we send signals of different frequencies. The other thing is that like soil has like different soil has like multiple the soil composition is actually very complex, right? There is actually air pockets, there is like stones, there is like other minerals, like salt is kind of like a major composition there. So everything affects your reflection of the signal, right? So in order to actually like separate out the reflections caused by all the major components, that's the reason why we use different frequencies. So we actually like send this multi-band of including both RF, Wi-Fi 2.4, Wi-Fi 5 gigahertz. We send these multiple frequencies and we look at the reflections for different compositions of the lead. And then we create a model to actually estimate the lead in the presence of all the other elements in the soil. And we kind of like showed that we will be able to identify the soil that has higher content of lead, which actually like labels that soil sample as kind of like dangerous and should not be in contact with any people. So that's how that system works.
Thank you. That was very clear. We're coming up to the hour, so there are no more questions on the chat. So I thank you, Raja, again for this wonderful talk. I hope to see you around the conferences, and I thank the audience. This was the last talk of the academic year. We'll resume in the next academic year. Thanks, everyone. Bye-bye.
Thank you.
Bye, Raja.